Asymptotes and discontinuities of rational functions. There are two types of discontinuities. One are non-removable, and we have seen these before and called them vertical asymptotes. For example, if y equals x plus 4 over x minus 2, let's set the denominator equal to 0 and solve for x. We get x equals 2. This is a vertical asymptote. So if we look at the graph, we see this graph of a reciprocal function with an asymptote at x equals 2. So we need to lift our pen or pencil when we're drawing this graph. This is a discontinuous graph at x equals 2. The second type are called removable discontinuities. We often call these holes, and you'll see why momentarily. For example, if we've got y equals x plus 3 times x plus 2 over x plus 2, we see a factor that cancels in both the numerator and the denominator. When this happens, we want to set that factor that cancels equal to 0 and solve for x. Here we get x equals negative 2. If we do cancel that factor, we get the function y equals x plus 3. So if we look at this graph, we see a hole, an open circle, a removable discontinuity at x equals negative 2. And to find the y value of that coordinate, we're going to substitute negative 2 in for x in our simplified function. So y equals negative 2 plus 3, or 1. So our removable discontinuity, our hole, has coordinate negative 2, 1. Okay, there are some key features that you need to know about asymptotes, about horizontal asymptotes for rational functions. So if we have a rational function with a numerator of degree m and a denominator of degree n, then we have a horizontal asymptote at y equals 0, the x-axis, if m is less than n. That is, if the degree of the numerator is less than the degree of the denominator. We have no horizontal asymptote if m is greater than n. So if the degree of the numerator is greater than the degree of the denominator. We will look at examples of these together in class, and instead of having a horizontal asymptote, these functions usually have an oblique asymptote, which is an asymptote at a slant or at an angle. A third possibility is that we have a horizontal asymptote at y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. And that occurs if m equals n, if the degrees of the numerator and denominator are equal. Okay, so let's look at this function. Y equals x plus 3 times x minus 2 over x minus 2 times x plus 1. First, let's find any removable discontinuities, or holes. So here's our function, and is there a factor in the numerator and denominator that cancels? Yes, x minus 2. We're going to set the factor that cancels equal to 0 and solve for x. So x minus 2 is set equal to 0, solve for x, we get x equals 2. We have a hole at x equals 2. To find the y value of the hole, cancel the factors and substitute. So if we cancel x minus 2's in the numerator and denominator, we get y equals x plus 3 over x plus 1. And if we substitute 2 in for x, we get y equals 2 plus 3 over 2 plus 1, which is y equals 5/3. So we have a hole at the coordinate 2, 5/3. Okay, next, let's find any vertical asymptotes. Remember, this is our starting function. And if we cancel factors, we're left with y equals x plus 3 over x plus 1. Let's look at the factor in the denominator that did not cancel. So let's take our x plus 1 and set it equal to 0 and solve for x. X plus 1 equals 0, subtract 1s, x equals negative 1. We have a vertical asymptote at x equals negative 1. Let's find any horizontal asymptotes. So this is our starting function. If we were to FOIL this out, we would have y equals x squared plus x minus 6 over x squared minus x minus 2. The degree of the numerator is 2, and the degree of the denominator is 2. So m equals n. So we need to look at leading coefficients. In the numerator, that's 1. In the denominator, that's 1. So we have a horizontal asymptote at y equals 1 over 1, or y equals 1. Okay, next, let's find the x and y intercepts. So remember, we're using this function, and x for y-intercepts, we set x equal to 0. So I get y equals 0 plus 3 times 0 minus 2 over 0 minus 2 times 0 plus 1. And we get y equals 3. So we have a y-intercept at 0, 3. To find the x-intercept, set y equal to 0. So 0 equals x plus 3 times x minus 2 over x minus 2 times x plus 1. We want to cancel factors if we can. So 0 equals x plus 3 over x plus 1. So for x plus 3 over x plus 1 to equal 0, its numerator must equal 0. So we're going to set this numerator equal to 0. X plus 3 equals 0. Solve for x. X is negative 3. So we have an x-intercept at negative 3, 0. So finally, let's sketch the function. Okay, so putting my scale on, every grid line represents 1. Here's our hole at 2, 5/3. Here's our vertical asymptote at x equals negative 1. Here's our horizontal asymptote at y equals 1. Here's our y-intercept, 0, 3. Here's our x-intercept. And let's sketch this in. And we can use our calculators to help us get the feel for the shape of this function.